Yep.
And the normal force going up.
Yep. You can use lowercase n or capital N, whatever. How do the magnitudes of these two vectors compare? Yep. How do you know? Another way of saying that is the net force is 0. I like how you said it though. Okay, what else? What about this one? What about a swing?
Tensions on the board going 2 to 1.
Uh-huh.
Normal force is going up straight.
Up straight from the ground, so maybe perpendicular from the ground?
Yeah.
Okay.
And then MG is going straight up.
Okay. Let's see. I want to break this into components. How should I set x and y?
Parallel with the surface.
Parallel to the surface.
And then y.
Well,
Y is
what were you going to say, Andrew?
y.
Andrew, what were you going to say?
Y is up.
What is up? That?
Perpendicular to the
Yeah.
that one.
You'd be surprised how many people, when they have to do the magic L, forget that x and y are perpendicular. I'll have people just like, let's try and do something like this. That's x, that's y. That doesn't work. No. X and y are always perpendicular, right? So when I tell you x is always parallel to the surface, you know that y is therefore always perpendicular to the surface, to x. Good. I'm going to change that rule next unit. I keep reminding you because I don't want you to go on my face when I do. Okay, let's see, Tony. I got to break something up into components. What should I break up? Okay, the mg one. Cool. So I'll just go ahead and do that. And we just learned that if this is theta, then this is theta, right?
Yeah.
We just learned that. Now, this vector is being canceled out by what other vector? Tension. And this vector is causing what reaction? Normal force. Right? Nature's lazy. Normal force is only going to push as hard as it has to. But if I push down harder on my mug, then the normal force is going to do what?
Get larger.
Get larger. Yes.
How do you know that the x component of force of gravity cancels out with tension?
How do I know? Somebody tell me. How do I make that conclusion, Raquel?
The rope is like tightened. It's the rock's not moving, so
It's equilibrium.
it's equilibrium.
It's at equilibrium, right? I know that. Sum of forces in the x equals 0, right? And so if I list my x forces, like that, and that's the only two I've got. And they're opposite directions, so it'll be t minus mg sine theta. There you go.
Okay, thank you.
Yep. Are we good on this one? Or just jump on? Okay. Bailey.
Okay. There's mg coming down on the
Yep.
rock.
Uh-huh.
Normal force pointing up from the floor.
Yep.
And there is another force, normal force coming from the other block going out.
Right, they're both normal forces. Are they the same value, do you think? No, let's call them N1 and N2 so we know they're not the same. Now, at a specific theta, they will be the same. At what theta will they be?
45 degrees.
45 degrees, they'll be equal, right? Do y'all see that? All right, Sylvia, what do I need to break up? Tell me this. The mg, good. For me?
Of course.
Jennifer.
Brett.
Happy birthday again.
Yeah.
2 days in a row.
It's 2 days in a row.
You were born on 2 days?
Yeah.
Go back in.
Wait, so.
Oh, no,
She's like, okay, you ready to move on? Yes. How is it N1 and N2? So is the question, how is this a normal force, or is the question, how are they different? Both. Good. All right, we've got the questions. Mr. Cameron, you get to answer one of them. Why are they different, or why is this a normal force pointing parallel to the surface?
Why are the normal forces
geometric
Yeah,
circle
because,
with two phases of equal.
MG isn't the MG components aren't spread equally between the X and the Y axis, so the, in MG is it has a larger component, for one axis than the other, so since the normal force only works as hard as it has to, then, there will be a larger normal force to, counteract the larger component and a smaller one for the smaller component.
Good. Another way of saying that, guys, this does not equal this in magnitude. Right? The only time they are equal is at 45, 45, 90 China. Okay, why is this a normal force, Alex?
Because the rock's leaning against the wall. So the wall's pushing back because the wall doesn't want the rock to switch through it.
Exactly. The wall says, we're getting too close. In lieu of you passing through me, I'm going to push back.
Personal space.
Yeah, personal space issues. Okay, we ready to move on? Good. Alright, this one's easy. Rock sliding on a frictionless incline. We've got mg. We've got normal force. Anything else? Is there another force?
No.
You know what some people like to try and draw? They're like, oh yeah, there's the force of the going. The force of the acceleration of the slide. No, that does not exist. Reject that force. I know, I discovered that earlier. Okay, we need to get out of here though. Stay away.
You're using the force.
Oh, that's cool.
So, I want you to just remember this rule of thumb. If you cannot identify what's causing a force, then it's probably not there.
Jedi.
People like to, Jedi's, it's probably not there. We only have one force, I'll give you a second, one force that's not a contact force. What's a contact force? Touching. Yeah, a force that involves touching. What's the one force that we have that's not a contact force?
Nuclear.
You're right. Okay, you're all saying all the correct answers. There's only one that we're using at this point in the course. Gravity. At this point in the course, we've only got gravity. It's our only long-range force. All the other forces involve touching. So if you want to draw a force of the go down the incline, a force of the push, then you're probably doing something wrong if you cannot identify what it is. And a lot of times I'll look at the two-body diagrams and I'll say, well, what's that? And you're like, oh, it's a force. And then you'll feel the awkwardness building and you're like, God, he's questioning me again. I'm having to think. Why doesn't he just tell me the answer? And then when you think about it, you'll come up with the answer. Man. Okay. Rock is falling, no friction. What's my force? Oh, Andrew had a question. Yes.
Going back to the previous one.
Yeah.
What you were talking about the force of the going or
The imaginary force?
That would be the resultant force, though.
Yes, it would. Okay, so let's draw what that looks like. Right? I can do the head to tail method. I'm just gonna. Interesting.
Would you move the mg up to this one?
Yeah, sine theta.
I can just do this. I'll just do parallelogram. And so then this is my resultant vector.
And that's the force.
That's the direction of my net force.
That's
my
the
two-
Yoda force.
No, that's a normal force. It's just it's a regular force. Nothing Yoda about it. It's not even green.
Is that net force?
Yeah.
Yeah.
Okay. Lovey, tell me what force is acting here.
MG's going down.
Okay, what else?
The number 12 is the first one.
Nothing else?
Nothing else. Good job.
Yay.
Let's see. Joanne, what does this one look like? Okay, what else? Okay, good. What else? Okay, good.
Can I do the next one?
Yes, you can.
Wait, but
Alright.
how is it moving then?
So what?
On the last one, how is it moving?
How is it moving? How is it moving?
Isn't that
There's-
equilibrium?
Hold on, we're going to think about it. Isn't it what?
Equilibrium?
Yeah, it's an equilibrium.
Then why is it moving?
We have two kinds of equilibrium.
X and Y. Oh,
Tell me the two kinds of equilibrium.
X and Y.
No! What are the two kinds of equilibrium? It's dynamic and, yeah. Static and dynamic. Which one is this one? Dynamic, cool. Alright, so this bothers people a lot, so you're not unique in this issue you've got with the picture. basically something got it moving at a time we don't care about. And from the time we start looking at it, constant velocity. Mr. Cameron.
Equilibrium is when acceleration is 0, right?
Yes.
So then, if number 10 is falling, wouldn't it be accelerating due to gravity?
Yeah, it's not in equilibrium.
Oh.
Right? Rock is falling, no friction. We're not at equilibrium.
Okay.
Sum of forces equals mg. And equals mg.
Still for number 9, since it is dynamic equilibrium, but there should be a force acting on it.
There are two forces, normal force and mg. There's no net force.
But it is moving.
Right, at a constant velocity.
Yes, since there is no friction, should we assume
No, we're good. This is correct. Okay, rock is falling at a constant velocity. Oh, wait, he called it. Sorry. He.
We're done.
No.
That's it.
Keel.
there's a normal force going upwards and mg going downwards?
Okay, there is an mg going down,
Well,
and I'm not
resistance
gonna,
friction.
it's not a normal force because normal forces only occur at surfaces. So if something's not touching a surface,
Air resistance.
yeah. Okay. Now I just told you, so the friction due to the drag. I just told you that there's only one long-range force. But here we seem to have a magical force showing up out of nowhere, touching our rock. Let's let someone else go for it. Well, where do you think this is coming from?
Reverse gravity.
Reverse gravity? Air resistance. Teach me your powers. What is air resistance?
Friction.
What is it? Now, just think air resistance. Focus on that. What is air resistance?
Air's
friction.
basically getting in the way.
Well, what does that mean? Air is getting in the way.
It's slowing you
Someone raise
down.
your hand and tell me. What does it mean? It's, oh, yeah, obviously it's slowing you down. Natalie.
There's pushing on you.
What is that?
Opposite direction.
What is air?
There's
It's what?
the fluid surrounding us.
The fluid surrounding us, okay. So let's, instead of thinking of it as a fluid, let's think about it as a bunch of discrete particles. Let's take a molecular approach. Now, as you're passing through air, it's kind of like running through a room full of ping pong balls floating everywhere, right? Every time you hit a ping pong ball, you're going to slow down just a little bit. But there's like billions of really tiny ping pong balls all flying around the room, right? And so as you get faster and faster, that air resistance is just the impacts from all those tiny ping pong balls hitting you. That's what air resistance is. So it's still a contact force. It's not a long-range force. It's the contact of hitting nitrogen and oxygen and everything else that's floating around in the air, CO2.
So it's just a higher pressure. Higher pressure. Oh, yeah, I got it.
Okay.
This is dynamic equilibrium, right?
Yes, it is. All right, number 13. Rock is decelerating because of kinetic friction. Arnold.
There's a mg going down.
Yeah?
There's a normal force going up,
Yeah?
and there's friction to the left.
Why to the left?
Oh.
Ty?
Because it says it's decelerating, so I don't know.
That's a good way of saying it. Good. I like that explanation. And then you can also remember that friction always opposes motion or desired motion. If you say it, we're a little bit more engaged. Friction always friction always opposes motion or desired motion. In the example of opposing desired motion, that's like number whatever, something on the front where it's sitting on the slope and it's not slipping, right? It wants to slip down, right? If we personify the block. The block wants to slip down, but friction says, don't slip, and it opposes that. Cool? Any questions on this one? And what kind of friction is this?
Kinetic.
Kinetic friction. Kinetic means motion, right? Rock is rising in a parabolic trajectory. Liminal. Tell me what the force diagram is on this one.
I'm guessing it's weight down, which is, basically already there. Mg is pointing down, and there's a friction force pointing towards the way it just came from.
Yeah, if there's air resistance, but we're going to assume no air resistance. So in every problem, assume no air resistance unless explicitly stated otherwise. Same rules as the last unit. But yeah, if there was drag, it would look like this. Yep.
That's it?
That's it? Yeah. Oh, Dad, did you draw the magical force of going?
No.
Okay, just checking.
Yeah.
It's okay. It's okay if you did. It's cool. All right, just don't do it next time.
I didn't do it. Yeah,
Suna, what does this one look like?
There's FD going down.
Uh-huh.
That's all I got.
And you're right. No. Why is there no normal force? What is normal force?
Again,
Jeannie, what is normal force? Tell me, just think about it. Yesterday, when we were talking about normal force, I ran over here and I talked about the 4 fundamental forces because I felt like that related to normal force because I wanted to explain it. Which of the 4 fundamental forces is normal force? There's 4. 4 forces are gravity, electromagnetism, strong nuclear, weak nuclear.
Electromagnetic.
Yeah. So it only happens when these atoms are being pressed on each other, right? You have to have a surface. No surface, no normal force. Oh, this is the one with an imaginary string. Imagination over. Okay. Rock is tied to a rope and pulled straight upwards, accelerating 9.8.
Well, I have not about this, just a quick, normal question. Does water have like a little bit of normal force?
Buoyant force.
So like the buoyant force is what makes like belly flops hurt?
No, let's talk about that during fluids. Omar, what is my diagram? You look so mad. What does my diagram look like for this one?
and you pointing down.
Yeah, what else?
I don't know.
Alright, that's fine. Akil, help him out. Hey, if you're stuck, just think the net force points which way? The net force points up. So I need to have something that's not just going to cancel this out, but give me a net upward direction. So what do you think, Akil?
Tension.
Yeah? How big is tension compared to mg?
Equal.
Double.
Equal? Double?
Double.
A little less than double.
A little less than double? Let's figure it out.
It's just big.
Okay, let's list my forces in the y direction. I've got positive t, negative mg. Sum of forces equals ma. My 2 forces are t minus mg equals ma. T is equal to mg plus ma. A is equal to g, therefore t is equal to 2mg.
Well, A is where'd you get?
Oh, A is
Because
9.8.
so what?
If there's
I mean,
Does that make sense? You see how we used our rules to get that? Awesome.
Oh, it's accelerating. Wait, can you go back?
Yes, I can go back. Give me a big thumbs up when you're done.
Mr. Landers, technically isn't that a little bit less than?
Why?
9.8 is less than 9.81. Sorry, Cat was just saying I was wrong.
Rock is tied to a rope and pulls a bit moves horizontally at a constant velocity. There must be friction.
Is that like supposed to be inequality?
No, it's not. That's a good question. This is just like the air moving around the rock. So, guys, tell me. Here's the rock tied to a rope moving at constant velocity. Emily, you try this one. What are my forces?
Mg is pointing straight down,
Yeah.
tension is pointing in the direction of the rope,
Yep.
and then friction is moving back from the center.
Yes. Why back?
Because it moves in the opposite direction of the movement you're trying to make.
Yes. Okay. Let's talk about why. This is at equilibrium. Yeah.
Why is there a T on the rope if it's moving at a constant velocity?
I'll tell you.
Why did you put a F not?
This is an FD. I'm sorry. F force is friction, drag, friction, drag, drag friction, drag force.
I thought it was going to do that.
I'll show you why. Because I need my sum of forces in the x and sum of forces in the y to cancel out, right? And so if that's supposed to be, there we go. That canceling out gravity, Alex. These two cancel out, these two cancel
Like,
out.
I see why that makes sense like that, but like, I don't understand conceptually, like, if velocity is constant.
Because the drag force is pulling it back and tension's pulling it forward. And gravity's pulling it down and tension's pulling it up. Rock is tied to a rope and pulled so that it accelerates horizontally at 2g. Patrick, see what you can do.
Did we see this?
Nope. The last one was at equilibrium.
Oh. Okay, well, energy swing straight down.
Yep.
Tension is going in the direction where the rope is coming from.
Yep.
And there's friction, or no friction. Oh, no friction. Okay. Yeah.
So you done?
Yeah.
Cool. And check it out. This is why it's accelerating. In which direction? X or Y? X, right? If we set our mind to go like that. So here's the X direction. Here's the Y direction. The magnitude of this vector is 2. Well, the magnitude of the acceleration is 2g in this direction, right? So the magnitude of this vector should be 2ng. Cool. Is that the last one?
Yes.
Good, because the rest of these I have on this PowerPoint are for circular motion. Microscopic interaction between the surfaces. And you can imagine that on the microscopic scale, all surfaces are not actually smooth, but they're like microscopic mountains. And when you're rubbing two things together, it's like the Rockies folded on top of each other, Inception style, right? You just like see the whole Rocky Mountains fold down on top of each other, and then they like rub back and forth, and you have like things breaking on each other, and that's a simplified explanation, but it works for your understanding if we take that model and put it on the microscopic scale about why it's hard to push something across the surface. I've told you there's two kinds of friction. What are they? Static and kinetic. So we've got static friction, and that's the friction. And kinetic friction is the friction while moving. Now, based on what you just did in the worksheet and some observations in the rest of class, what have you learned about static friction? What is special about it? How hard does it work?
It's harder than these two.
Okay, so give me an example of that.
If you're pushing something and you're not pushing it very hard, and because you're not pushing it very hard, the surface could still stop it if you're pushing it harder, but it's only going to work as hard as it needs to.
Okay, Bailey?
Like if I'm pushing on a calculator, it's not pushing back more than I'm pushing at it
Right.
because it's staying in one spot. So I'm exerting like, let's say 2 newtons or something on it, then it's going to start moving.
Good.
Its limit is lower.
Alex? That's good. Oh, sorry, I thought you were done. Come on.
Yeah, that's it.
Alex?
Isn't it pretty much the same thing as normal force?
No. It's related though. It is related. So if I was going to do a graph of friction versus maybe the force of how hard you're pushing on an object. Okay? So we've got you pushing on, I don't know, what are you going to push on?
This is Landers.
What?
Ball.
An elephant.
This is not an elephant unless I give it like,
Wait, you said an elephant's just a box?
now it's an elephant. Okay? Alright, we've got an elephant box. Now, we're going to do a graph of you. You're very close, don't worry. There we go. And you're not bald. Okay, you're pushing on this elephant box, and as you push, initially it's not moving, okay? So what should my frictional force versus how hard you push graph look like?
0 at the origin.
0 at the origin, and then what? Increasing, and what's the slope of that increasing line?
1.
Right, that's a slope of 1 because they're meeting, right? So we're going to put, oh shoot,
M equals 1?
thank you. M equals 1, we know what M is.
Yeah.
Okay, until all of a sudden your elephant box starts to move.
And then it's a flat line.
Then it's a flat line. Now I have a question. Is it easier to get something started moving or to keep it moving?
Keep it
Get it
moving.
started.
Keep it moving.
Wow, there's a debate. Well, actually, it's much easier to keep it moving. And the reason isn't entirely what I'm about to show you. Part of it is Newton's first law. An object in motion wants to stay in motion, an object in rest wants to stay at rest, right? But a lot of it is this, that we reach some maximum static frictional force and then we drop down. So this is called the maximum static frictional force. So it's a lowercase f with s subscript, and this one is lowercase f with a k subscript. And so here I've got the kinetic frictional force, which is what? What can you tell me about it?
It's lower than this.
It's opposing to direct motion. It's also constant. That's something that truly sets it apart from the static frictional force. The kinetic friction is constant, no matter how hard you're pushing, no matter how fast you're going. Kinetic friction is constant for what you're concerned with. Now, is it easier to push this elephant box on ice or on a rubber floor?
Ice.
Ice. So what do you think affects the force of friction?
It's texture.
Texture, temperature, is that what someone said? Maybe material? We said material maybe? So the material relationship that we associate with the force of friction is called the coefficient of friction. And we have coefficients of friction for static and coefficients of friction for kinetic. So the static coefficient of friction obviously is a little bigger, right, than the kinetic coefficient of friction. This only relates to, oh, whoops. This only relates to the maximum force of static friction.
So those are all maximum values?
Well, no. They're all the static coefficient of friction. The coefficient of static friction is the same for waxed ski on snow, whether or not you're at the max value or not. But you can only calculate the max value using that. So like Fs max is the only place where, what Greek letter is this? Mu. Mu. Where the coefficient of static friction applies. I haven't given you the equation yet. I need to erase the elephant box for the sake of space. Okay. So what else do you think affects the force of friction? Why do you think the normal force affects it?
Because it's perpendicular.
Because it's perpendicular, because it's pushing away. Andrew?
Because if the texture is all jagged, then there's going to be normal forces all over the place, and some of them will be pushing in the opposite direction than what you want your object to go.
Okay.
Because like he said, since it's jagged, like it connects like that, when you're trying to push this way, these ones will push it back.
Okay, good. So why does normal force affect it though?
Because the normal force is what sort of pushes it.
Okay. Is it easier to push an elephant box or a box full of feathers? Box full of feathers. Why?
Because it's legless.
So what?
So the normal force isn't as strong.
So the normal force isn't as strong. How about this? If I try and push Julie's book across this table, you know, I can observe about how hard this is to push, right? But now if I press down on top of it and try and push it across the table, it's a lot harder. What have I done by pressing down on the top of the book? Increase the normal force. So what have I done on the, what have I done on the microscopic level? Smash them together, right? So it's harder to get it moving. So normal force affects it, coefficient of friction affects it, that's it. Here's our equation for the maximum force of static friction. here's our equation for the force of kinetic friction. You can only calculate the maximum the maximum force of static friction is calculated using the coefficient of static friction. You can't calculate the force of static friction during this interval using the coefficient of static friction. It's such a common mistake among students. That's why I say it so often. I don't want you thinking you can use mu unless you're at the maximum. In a problem, it's usually stated like this. What angle can I put the textbook at before the car slips? How do we find that? Well, the car slipped at the maximum force of static friction.
What are the subscripts on the U?
S and K. Same as the subscripts on the forces. And this is S max, SMAX. It's like a serial. Yes, ma'am.
So you can only find FS if you are using FS max. You can't find it anywhere else except if you have.
Well, I could find FS if I don't know FS max, right? I'm pushing on this book at 1 Newton. How much is the force of static friction?
1 Newton.
Because it's not moving. It's going to push as hard as it needs to. For Kitty, you had a question?
Oh yeah, what's N?
Normal force.
So you can only use mu S at the maximum. You can't use it anywhere else.
Right. Normal force. Now, this is important. When the object is on a flat surface, what is normal force equal to? mg, the force of gravity, right? And this was on your worksheet. As the angle increases, what does the force of gravity do?
It becomes more effective. Less effective.
I'm sorry. Did I say normal force? As the angle increases, what does the normal force do? What is the normal force on my car when we're at 90 degrees?
Very little.
No, it's 0. When we're at 90 degrees, it's 0. And here, normal force is mg, right? This is 0 degrees. What's the cosine of 0?
1.
What's the cosine of 90? 0. So normal force is always mg cosine theta. That was in the warm-up. Well, always as long as I'm not like, pulling on it with the rope or pushing down on it. So always with lots of caveats on there, right? But we can say, for the sake of just a block on a slope, something that simple, normal force is mg cosine theta. Yeah, cosine, just checking. mg cosine theta. Here theta is 0, so normal force is mg. Here theta is 90, so normal force is 0. So frictional force. The maximum force of static friction is going to change as well as the angle tilts up, because it's dependent upon normal force. I like to write the coefficient. We're not going to get to the problem I got to do in the second block, I'm sorry. I like to write this like this, because I think it proves an interesting point. That, first of all, what are the units for the coefficient of friction? Do dimensional analysis. Do dimensional analysis real quick, look at it. What are my units for the coefficient of friction? Oh, is it a kilo?
None.
It's none. Why?
Coefficient's not even.
Oh, okay, that's an okay reason. Use dimensional analysis and tell me why it has no units.
Both are forces.
The same people are always answering my questions. I need someone new. I need a new person. Yeah.
Is it a ratio?
It is. Oh, that's all I can think
Like,
about
because
that.
the top one, the static force at the maximum level is also measured in newtons, and so below it's in newtons, so they cancel each other out.
Exactly. They're both in newtons. Newtons cancel. No units here. Got it? And then look at our optional values. It tends to be between what two values? What would you guess?
0.
0 and 1. Looks like our coefficients of friction are between 0 and 1. What does it mean if
Yes,
it's greater
that's max.
than 1? What does it mean if the coefficient of friction is greater than 1?
Then the mass is really
Okay.
Does that mean that the force it takes to get it moving is greater than how much it weighs?
Yeah. So
So
basically,
it takes more force to do this than this?
yeah, it takes more force to push it across whatever surface you're on than it does to lift it straight up.
Only if it's greater than 1.
Only if the coefficient of
Static.
static or kinetic in either case, right? But it's just saying if it's greater than 1, it's easier to apply a force to mg than to mu n. You can remember this because look, physics is fun. Okay. We have a minute and a half. I'm gonna solve this problem like lightning so that you'll have seen it, and I'll go over it later. And Sabrina's gonna just do the video in slow motion so you can see it later. Okay, so we have a seal on a slope. He's sliding down. I am going to solve for the acceleration in terms of just these variables. I want to find acceleration in terms of m, g, theta, and mu k, the coefficient of kinetic friction. This is similar to a problem in your book. This is a picture straight out of your textbook. All right, so free body diagram for Senor Seal. Normal force. There's the weight. Here's the force of kinetic friction. He is accelerating down the slope. The force of kinetic friction is just counteracting the weight a little bit. So if I break weight up into y and x, this force is in the x direction. I say that it's negative, I say that's positive, F. I'll just do it later.